All right, let's dive right in. Today, we're going on a trip, but not into space. We're going deep inside the rocky planets in our own solar system. We're going to uncover the massive forces that build them, shape them, and ultimately decide what they become.
So here's the big puzzle, right? You've got Earth, Venus, and Mars. They're basically siblings, born from the exact same cloud of cosmic dust. But look at them now. One is our dynamic, living home. Another is a volcanic, toxic furnace. And the third is just a frozen desert. How in the world does that happen? How do three planetary siblings end up so incredibly different? Well, the answer isn't on the surface. We've got to go deep, deep inside.
To really crack this mystery, we have to look at the engine that's powering all of these rocky worlds. And it's an engine that doesn't run on gasoline, but on pure, raw heat. This one idea changes everything. A planet isn't just a big, dead ball of rock. It's an engine, a thermodynamic engine that is constantly trying to get rid of the incredible heat that's trapped inside it. Heat from radioactive elements decaying and just leftover heat from when it first formed. And it turns out the way a planet gets rid of this heat, well, that defines everything about its personality.
And the main way planets do this is through a process called subsolidus mantle convection. I know, it sounds super technical, but subsolidus just means the rock is technically solid. But, and this is the wild part, it's so insanely hot and under so much pressure that it can actually flow, kind of like super thick molasses, just over millions and millions of years. This slow churning motion, that is the planet's engine.
So how's it work? Just picture a giant planetary-scale lava lamp running in super slow motion. Heat from the core and from radioactive decay warms up the rock deep down in the mantle. That makes it a little bit less dense, a little more buoyant, so it starts to slowly rise. Once it gets near the surface, it loses its heat to space, cools off, and gets dense again. And what does dense stuff do? It sinks. It falls right back down toward the core to get reheated, and the whole cycle starts over. This happens on every rocky world, but the way it shows up on the surface, that's where things get interesting.
Okay, so let's start with our home turf, Earth. Here, that internal engine is running like a really smooth, really efficient conveyor belt.
On our planet, that churning mantle is directly connected to the crust. See, Earth's surface isn't one solid piece. It's shattered into these huge tectonic plates. And those plates are literally the cold tops of these convection cells, getting dragged around. They're constantly moving, grinding past each other, pulling apart, smashing together, and this whole process lets Earth's internal heat escape in a pretty steady, continuous way.
And this is the result. It's amazing. Plate tectonics is basically a planetary recycling system. You have new oceanic crust being born all the time at mid-ocean ridges, and then it gets destroyed when it dives back into the mantle at subduction zones. That's why it's so young. Meanwhile, the lighter continental crust is like, nope, not sinking, so it just bobs around for billions of years, preserving this incredibly ancient rock. This two-part age story is totally unique to Earth.
All right, now let's hop over to our so-called sister planet, Venus. If Earth is a conveyor belt, Venus is a ticking time bomb. It's a planetary pressure cooker.
See, Venus has no plate tectonics. Its crust is just one single solid lid. So even though it's got that same heat engine churning away deep inside, that heat has nowhere to go. It just builds and builds and builds up underneath that lid, like steam inside a sealed pot.
So what happens when that pressure gets to be too much? Well, by counting craters on the surface, scientists have figured out that around 750 million years ago, the entire surface of Venus was violently repaved by volcanoes. The pressure cooker blew its top big time.
This is the leading theory for how Venus works. As all that heat builds up from below, the crust on top just gets thicker and colder. Eventually, this heavy lid becomes so dense and unstable that it just can't hold itself up anymore. It cracks, shatters, and sinks into the mantle all at once, triggering a planet-wide flood of lava that just erases the entire surface.
And believe it or not, we've actually seen a mini version of this happen right here on Earth. Scientists watching a lava lake saw the solid crust that formed on top just suddenly and spectacularly break apart and sink into the molten lava below. Now imagine that, but on a scale that covers an entire planet. That's Venus for you.
So, finally, let's look at the little guys, Mars and the Moon. If Venus's engine is unstable and explosive, theirs are just, well, they're running out of juice.
It really comes down to size. Because they're smaller, Mars and the Moon just couldn't hold on to their internal heat for as long as Earth and Venus. They cooled off much, much faster. Their engines have slowed to a crawl, and as a result, any major volcanic or tectonic activity basically shut down billions of years ago. They are now very, very quiet worlds.
But what's left behind is this incredible planetary scar, what we call the hemispheric dichotomy. Both worlds are basically split right in two. One half is ancient, super high, and just battered with craters. That's the original crust. And the other half is younger, lower, and smoother, covered in these vast volcanic plains that erupted back when the engine was still running hot.
Check this out. This is the height of Olympus Mons, the tallest volcano in the entire solar system, and its insane size is a direct result of Mars having a dead crust. On Earth, our moving plates create a chain of smaller volcanoes, like the Hawaiian Islands. But on Mars, the crust just sat completely still over a mantle hotspot for maybe hundreds of millions of years, letting a single volcano grow to be absolutely gigantic.
And the Moon's story wrapped up even earlier. Once those last huge lava flows poured out and filled the basins on the side facing us, its engine pretty much turned off for good. For the last 3 billion years, the Moon has basically been a dead planet, its surface only changed by the occasional asteroid impact. It's a quiet relic.
So, let's put all the pieces together. You have one fundamental process, but it tells 4 totally different stories across our solar system.
And it all comes down to this. The exact same engine, that slow churning of the mantle, is running inside all of these worlds. But a planet's size and what its crust is doing changes everything. Earth's engine runs steady, recycling its surface. Venus's engine builds up pressure and then catastrophically boils over. And the engines on Mars and the Moon have pretty much run out of steam, leaving behind ancient scars. In the end, a planet's entire destiny is written by the simple story of how it loses its heat.
And that just leaves us with this one last incredible thought. We've just seen how one single physical process can create a living paradise, a volcanic hellscape, and a frozen desert, all right here in our own cosmic neighborhood. It just makes you wonder, as we start discovering thousands of new rocky worlds orbiting other stars, what other unbelievable variations on this theme are still out there, just waiting for us to find them?